Hello and welcome to the first lesson on quadratic equations. Now, this is the first topic in secondary 3, additional mathematics. So, if you are a Sec 3 student watching this video, you should be no stranger to this topic because we already have done quadratic equations in secondary 2. So, before I start, you can see on the left-hand side, I guess, left-hand side, yeah, over here on this side, this side of the screen, yeah, you can see there's a checklist of the points that I would like to go through for this video. Right, as we go through, I'll try to tick them off one by one. So yeah, without further ado, let's jump into quadratic equations. So here are the notes. Sorry, wrong screen. Here are the notes over here. You can find the notes on Discord. If not, I might have put them up somewhere else for you to download, right? A PDF of this. So yeah, let's start off with what we already know, right? And we can see a meme over here. Yeah, the meme says me using the quadratic formula. Yes, this is the quadratic formula to find the roots of x squared minus 1. Yeah, and then you see a picture of Bill Gates. This is Bill Gates, the one on the left. And then there's Bernie Sanders, right? And they are playing table tennis, but Bill Gates is playing with a super huge bat, super huge ping pong bat, right? That is overkill. That's way too big for a small ball like this, right? So that's exactly what's happening over here. If you use quadratic formula to solve this equation, you are kind of using, too large of a tool for something so simple. All right. Yeah, I hope you enjoyed that meme. Now let's look at the next page. What is quadratic equations? What is the word quadratic? What does it even mean? So as you know, quadratic, the word, or rather English, is a Latin-based language. So the word quadratic actually comes from the Latin word quadrare, which means kind of means square, right? So when you're talking about quadratic, you're kind of implying things that are squarish. Yeah, squarish. Okay. Yep. Sorry about that squiggly handwriting. Yeah, squarish stuff. So quadratic equations, squarish. Let's look at examples of quadratic expressions, which you might know. Say this x squared plus 5x plus 6. This is a quadratic expression. Or we can also say things like x squared minus 1 or 5x squared plus 2x. All these are examples of quadratic expressions. And some of you might be thinking, oh, I see the pattern. There must be an x squared in any of these terms in your expression. And you're right. We should have an x squared. Okay, what happens when we don't have an x squared? Say, for example, I have taking the first one. Sorry, let's ignore this. I just remove the x squared, right? Let's say if I want to look at 5x plus 6. Now, this is no longer a quadratic equation expression. It is now a linear expression. Linear expression. Yeah. So we can see in the next page of our notes. Yeah. Let's do this over here. Let's put quadratic over here. Yeah. This is quadratic. And examples will be, x squared plus 5x plus 6. Okay, and then we have the general form over here in the middle column. Yeah, what does that mean? General form means that in general, all quadratic expressions can be represented by this. Yeah, ax squared plus bx plus c. This is what quadratic expressions look like, with the exception that a cannot be 0. And we have seen what happens when a equals to 0, right? When a equals to 0, we get a linear expression, yeah, where it becomes something like that, ax plus b. Yeah, do you remember the x squared plus 5x plus 6 example? If I remove the x squared, then it just becomes 5x plus 6. And then that goes into the category of linear expressions. Okay, so you notice that, hey, in this table, I have linear quadratic. There's 2 more spaces over here, right? What happens if I, say, drop the x term? What if I just have, a constant here? That's where you have a constant. Yeah, a constant. And I think this is the only exception where your a can be 0. Yeah, So let's write that down. This is the only exception. Huh? Only exception. Oh, the camera has acted up again. Yeah, camera's kind of strange, changing modes on its own. Sorry about that. So let's look at what goes beyond quadratic, right? What if we have things like ax cubed plus bx squared plus cx plus d? Yeah, what happens when we have this? That's when we have a cubic expression, a cubic expression. Yeah, so these are the names of the polynomials. Yeah, so now let's look at something else. I also included, if you notice over here, the degree of the polynomial, right? The degree. So this one is pretty straightforward. So the degree of a constant is 0, right? Because you can think of this as x to the power of what, right? This is x to the power of 0, isn't it, right? Linear is degree 1 because the highest power of x is x to the power 1. Quadratic is degree 2 because I have my highest, power of x is 2, and of course cubic is 3 because it goes up to x to the power 3. Yeah, so this is the polynomial family. Of course, we can go on to degree 4, degree 5. In fact, it goes on to infinity. Yeah, but we really just concern ourselves with quadratic and cubic in Sec 3 and Sec 4. Yeah, okay. You can fill in the examples of the cubic expression on your own, right? I'm going to move on to the next page, right? Now that we talk about expressions, what are equations? What's the difference between expressions and equations? And yeah, the word equation seems to imply, right? It looks like the word equal. Yes, so equations involves an equal sign. It involves a right-hand side. Yeah, we have an equal sign now. We have a right-hand side over here where there's a value assigned to this expression on the left. Yeah, good. So let's look at examples of quadratic equations. Yeah, the first one is a perfect example of a quadratic equation. X squared plus 5x plus 6 equals to 0. How do we know it's quadratic? Again, we look at the highest power of the letter here, x. The highest power is 2. That tells me that's a degree 2 polynomial, and then that's quadratic. Yeah? Okay, let's look at example number 2. How is it different? Now I've assigned a value of 10 on the right-hand side. Is this still a quadratic equation? The answer is yes. What we can do is we can take this 10, move it to the left-hand side, or you can think of it as subtracting by 10 on the left and right-hand side. So what we end up with is x squared plus 5x. That still remains the same. But now our 6 will have a negative 10, right? Plus 6 minus 10. So that gives us a negative 4. And this is equated to 0. Guess what? This second line is still a quadratic equation. So we still have a quadratic equation going on here. So let's put a green tick beside that. Example number 2. Good. That is also an equation. Now let's look at example 3. We can also do the same sort of manipulation. Bring in the 5x to the left-hand side. That becomes a negative 5x. So what we end up with is just an x squared, 0x, and plus 6. This is equals to 0. Now, is this a quadratic equation? Yes, it is, because the highest power of x goes up to 2. That is a quadratic equation. And finally, we look at the last example, example 4. We do the same sort of manipulation, right? We bring the x squared to the left-hand side. What happens is we have a negative x squared now. That gives us 5x plus 6 equals to 0. And you can see over here, this is not a quadratic equation. This is a linear equation. Yeah, so we got to be careful with that. Okay, although we started with a quadratic on the left, right? Sometimes it can reduce to a linear equation. So yeah, good example. Now let's move on to the next page. Okay, before I move on to the next page, I think we're kind of done with quadratic expression and quadratic equations. So I'm going to go ahead and check that off the first checkbox. Yeah, we're done with that. Now we're going to move on to functions. Yeah, we're going to move on to functions. So first of all, yeah, what are functions? You might have heard your teacher say functions before, right? Here and there. And one thing you might notice that they are very similar to equations, right? But first of all, I just want to say they are not the same as equations. They are not equations, although they are similar. Yeah, so we can fill that in. Right, there you go. Yeah, they are similar. Next, how are functions written in your textbooks or in your question papers? Yeah, it's written this way. We write a f and then bracket x. Okay, so now we know how to write functions. We can either use f or we can also use letters like g. You can use letters like f, g, h, I, j. Right? We usually start with f because the word function starts with f. Yeah, and other than knowing how to write this, we need to know how to read this. Because when you learn mathematics, you need to talk to your teachers, you need to ask questions, you need to ask your friends. You need to know how to call this thing, right? So this thing, if you read out, it is read as, okay, so a lot of students will say f bracket x. Huh? That's not correct. The correct way to call this is f of x. F of x, which means the one below will be g of x. Right, if you have the next one, there will be h of x, I of x, k of x, j of x, yeah, so on and so forth. That's how we read, and that's how we write functions. All right, next, let's try and understand how functions work. Right, how do they work? Right, we think of functions as machines. Yeah, it's a very simple machine. That's what functions are. Right. Okay, and you can see this machine is rather simple. It has one thing on top that allows you to put things in, the inputs. Yeah, the inputs over here. And then at the bottom of the machine, something comes out. That's the output. Yeah, so I thrown in an example here. If you put oranges into the machine, then orange juice or OJ comes out. Yeah, so it's a simple machine. The function of this machine is just to make orange juice from oranges. Okay, but of course in mathematics, we don't concern ourselves with fruits or oranges. We really want to know about numbers. So instead of putting oranges in, we can put things like numbers. Yeah, and usually the input is x and the output is known as f of x. Yeah, in this case, if x is 1, then I'll say the input is 1. So this is f of 1. F of 1. And then let's say that this is a +1 machine. Yeah, if I put 1 in, then what comes out? If I plus 1, then I get 2. Yeah, so this is a simple relationship. I put 1 in, I get 2 out. Yeah, put 1 in and I get 2 out. So if I put 2 in, then I'll get 3 out. Yeah, so let me just write that down. Yeah, if I put, say, 2, then f of 2 will be 3, so on and so forth. Okay, so this is what we do in mathematics. This is how we use functions. Okay, but of course, we have a lot of numbers. We are not just satisfied with looking at one pair of input and outputs. We want to look at a lot of pairs of inputs and outputs. So what we do is we actually have a table. Yeah, we can actually have a table and we do things like that. So let's put in, say, 3 values, x equals to 1, x equals to 2, x equals to 3. And the corresponding outputs will be f of 1 is 2, f of 2 is 3, and f of 3 will be 4. Yeah? Okay, so over here in bottom, we can summarize it with a table. So we can say that the input, which in this case is the letter x, right? And the output is f of x. Okay, if x is equals to 1, f of 1 will be 2. If the input is 2, the output will be 3. If the input is 3, the output will be 4. Yeah, sorry about the watermark there. Yeah, so hope you can see the 3 and the 4, huh? Okay, good. And other than using a table, there's also something else that gives us a very good, it's a very good tool for us to look at all the different inputs and outputs at one glance. And you might have guessed it, that is the graph, right? That is the graph. Very good, right? So if I were to plot the points out or of this graph, say when x equals to 1, y equals to 2, here's 1, so here's 2, right? Here's 1 point, And then when x equals to 2, y equals to 3, you get another point. X equals to 3, y equals to 4. Here's another point. And then if you plot this, you realize that, hey, you get a straight line graph, right? This is the axis for the output. This is the axis for the input, right? So your x-axis, and instead of the y-axis, you have the f of x-axis. And this graph is f of x equals to x plus 1, because it's a plus 1 function, right? So yeah, pretty cool, right? Functions, how they work. Okay, so yeah. Now the question that might be in some of your heads is that, hey, wait, don't equations do the same thing? Right? So let me just go back to the previous slide very quickly. And you don't have to do this on your notes. I just want to show this, right? What if I replace f of x with y? Yeah, let me just replace all of it with y. So y. Isn't that the same as an equation? I can just say that y is equals to x plus 1. Yeah. So what is the difference between functions and equations, right? So, right, here's the difference. On the next slide, let's draw it out, right? Functions versus equations. So first of all, you can see that functions have a very, very strict constraint that's being shown on the picture on the left, right? The constraint is this. For each input, sorry, let me use blue. For each input, right? We only have one output. Okay, so if you put something in, something else comes out. Like if you put orange in, OJ comes out. Yeah, you cannot put like oranges in and then maybe OJ comes out and then maybe orange cake can also come out. Yeah, it only has one output. If you put one thing in, you get one thing out. Now, let's look at equations. Equations, on the other hand, over here, we have a machine that's not a function, it's actually an equation. If you put something in, you might get two things out. Yeah. So for equations, multiple outputs are possible. For a single input. Okay. Yeah, so that is the very, very, very big difference between functions and equations. Okay, so let me just give you a very simple example. Let's go back to our plus 1 function. So for example, this function is such that x becomes x plus 1. Yes, so if you put in x, it becomes x plus 1. So if I put x equals to 1, you get f of 1 equals to 2. Yeah, you put in 1, you get 2, you put in 2, you get 3, so on and so forth. Yeah, so f of 1, x equals to 1, f of 1 equals to 2. Yeah, let's look at equations, right? Equations, for example, I have equations like this. Y squared equals to, say, 25. Yeah, so if I put 25 inside here, what are the possible values of y? Right? So you see that I need to take a square root. Y can be equals to square root, but that's a plus minus, right? Because, okay, so the answer is either 5 or negative 5. Okay, if y squared is 25, then y could be 5, because 5 times 5 is 25. At the same time, y can be negative 5, because negative 5 times negative 5 also gives you 25. So there are two possible outputs here. One is negative 5, one is 5. Yeah, so this is an example of a non-function. Yes, so we don't call the square root a function. We don't say, oh, the square root function. We say the square root operator, right? The square root operator, because there is a possibility of having two outputs. Yeah, simply put. Yes, good. So that is the very big difference between functions and equations. Yeah. Okay, so I'm going to go ahead and check off functions. Yes, on our checkbox, our checklist on the right, before moving on to roots. Right, that is the end of functions. Now, moving on to roots. Before we start on roots, I think the word roots is a bit, should be familiar to some of you. You might have heard of it before. But before we talk about roots, let's talk about this guy. What is his name? Okay, some of you might know from the picture, or some of you might know Carl Friedrich. And then you know the next word is Gauss. Yeah, this guy's name is Gauss. right? He's a very famous mathematician. He's responsible for a lot of things that we use today. For example, number 1 over here, right? I think you might have done this problem in primary school before. What is 1 plus 2 plus 3 plus 4 plus 5 plus all the way to 100? Yes. And then we had the rainbow method, right? Some of you know it as a rainbow method, where we pair the first and the last number. 1 plus 100 is 101, followed by 2 and 99 is 101. 3 plus 98 is 101. And we can continue pairing up all the numbers, right? And we realize that they will all form 101s. Yes. And you end up with 50 of them. Right? And then you get the answer, which is 5050. Yes. So Gauss is actually the person who invented this method. Yeah. When he was a primary school student, he invented this. Right. So if you want to look it up and read up more about Gauss, you can read up summation to hundreds. Yes, this is what you can Google. Summation to 100s. And remember to include his name, Gauss. Yeah, you can read about that. Okay. Another thing that he's responsible for what we use is if you ever use Instagram or use a photo filter to blur images. For example, you take a photo of yourself and you want to blur the background so that it gives a very professional look. Yeah, you have to thank Gauss because he is the one who invented the mathematics behind that, right? So if you want to look this up, sorry, there's a watermark here. So I'm going to write this over here. You can Google Gaussian blur. Gaussian blur. Yeah. So yeah, he's the guy for the maths behind that. So why are we talking about Gauss? Why are we talking about all these kinds of things when we're supposed to talk about roots? So you know what? He was the guy who came up with this. He proved that if your degree of your polynomial is 1, oops, sorry. Let me just remove those dots. If the degree of a polynomial is 1, meaning that it's linear, right? It looks like this. Then you have 1 root. Okay? If the degree of the polynomial is 2, meaning that you have things like that. Yes. Okay, let me put this in brackets. Yeah? Then you have 2 roots. If your degree of your polynomial is 3, where you go up to x to the power of 3, then you have 3 roots. Okay? So it is, sorry about this. It is not easy to prove this actually, yeah? But I just want to show you, right, something at a Sec 3 and Sec 4 level, how we can appreciate this, right? Why is it that, you know, the degree 2 polynomial has 2 roots, a degree 3 polynomial has 3 roots, so on and so forth. So first, let's talk about roots, right? What are roots? So if you think about roots, you probably think about a tree, right? A tree with roots, and the roots are usually sunken into the ground and they do not move, right? Most of the time they do not move, right? So let me just draw the ground over here. Yeah, pretend this is the ground. Okay. Now in mathematics, we also have roots, right? And I want you to think of the ground as the x-axis, Yeah. So let's also draw in the y-axis. Oops, sorry, that is not a very straight line. Please pardon the scratchy drawing. Yeah, so that's our x and y axis. I want you to think of the roots or the x-axis as the ground, and roots are something that gets stuck on the x-axis. All right. So next, let's look at simple graphs. Right. Let's look at one simple graph of f of x. Okay. How would you plot x minus 1? X minus 1. So let me bring out a straight line here. Okay, x minus 1 will look something like this. Okay, this is f of x equals to x minus 1. Okay, you can go back and revise your straight line graphs, how to plot straight line graphs. Okay, and since we are interested in the x-axis, which is the ground, and where this graph cuts the x-axis, right, we know that this is equals to 1. This graph of f of x will cut the x-axis or cut the ground at 1. So we can say the roots of this graph is at x equals to 1. So I'll say that one more time. The root of this graph, or the root of x minus 1, is at x x equals to 1. Yeah, that's where the root is. Now let's look at the second graph. Let's look at g of x. Again, I'm going to bring out a line. This time I'm going to use green because this is a separate graph. And there you go. It should look something like this. And let's name this graph. This is g of x equals to x minus 2. Right? And you can see it's going to cut the x-axis. It's going to cut the ground at x equals to 2. So the root of x minus 2 is at x equals to 2. Yes? It's at x equals to 2. All right? So, right. Any questions here? Okay. Seems quite straightforward, right? So, I have a question. Then where are the roots? Where are the roots of, say, x minus 1 times x minus 2? Where would it be? Yeah, this is something to think about, right? If the roots of x minus 1 is at 1 and the root of x minus 2 is at 2, then where would the roots of the multiplication of these two graphs be? Yeah, so I'm just going to very quickly show you a graph, which is decimals, on decimals here, right? I've actually gone ahead and plot the same graphs here. The one in red, which I'm toggling on and off here, is x minus 1. You can look at the left side of the screen, where I'm clicking on this red circle. It shows and hides the graph. You can see that, yes, indeed, this red graph will intersect the x-axis at x equals to 1. And for the blue graph over here, g of x, right, it's going to cut at x equals to 2. Right, there you go. These are the roots of the graph f of x and g of x. Now, before I click on the third line over here, this one, which will show the multiplication of x minus 1 times x minus 2, make a guess about where the roots is going to be. Okay, so I'm going to show it in 3, 2, 1. Here, this green graph is x minus 1 into x minus 2. And you can see the roots of this green graph is exactly the same as our two graphs over there. Yeah. In fact, I'm going to go ahead and do this, right? If you're interested in trying this out on your own, this is on decimals. If you're on Discord, our Discord server, right, I will also post up the link to this graph over there. So you can go and play with it on your own, right? What I'm going to do is I'm going to replace 2 with the letter A, so that I can change A. A doesn't have to be 2, right? I can slide it around. See? I can slide it around. I can slide it to, say, 3. Let's make it, say, 3. X equals to 3. So when x equals to 3, A equals to 3, you can see that my blue graph now cuts. Let me hide this green curve first. You can see my x-intercept, or my roots of the blue graph, is now at x equals to 3. And what follows is that the green graph also follows the roots there, right? So as I slide around, let me zoom out. As I slide this around, you realize that, hey, the roots of the green graph follows exactly the roots of the red and the blue graphs. Yeah. So one more time, right? The roots of the combined graph, the multiplication of the two linear graphs, is exactly the same as a linear graph. So we can say that the roots of a quadratic expression is the same as its linear components. Yes, because we know that this quadratic graph, fx times gx, let me just write it down back in our notes here. Okay, so if we sketch the graph, it'll look something like this. Yeah, a poor sketch, but yeah. Okay, this graph is equals to x minus 1, x minus 2. Yeah, so this will give us a quadratic if we expand it out, right? So we can say that the roots of a quadratic graph, right, is equal to its linear components, right? It is actually made out of this guy and this guy, right? You can think of them as ingredients, right? We put in these two ingredients, and what we get out, yes, like if you bake a cake, the cake that we bake has the same properties as the ingredients that we put in. Yeah, so that is really, really interesting. Huh? Okay, so the next question will be, why is that so? Why does the quadratic graph, right, have the same roots as its linear components? So let's look at this in terms of machines, right? Our functions again, right? This is why we learn about functions. So let's look at the two separate functions again. Yeah. If you remember this part, this is, this should be blue, come on. So this is our f of x. Remember, f of x is equals to x minus 1. And this side is our g of x, isn't it? Let's first look at what happens when we throw in values. We feed values in for functions x, f of x, right? When x equals to 1, 2, 3, f of, okay, so I should change this to f of 1, right? This is f of 1. Yeah. This is f of 1. This is f of 2. This is f of 3. There you go. F of 1 will be x minus 1. It will be 0. F of 2 will be 2 minus 1. That will be 1. F of 3 will be 3 minus 1. That is 2. Yeah. So in case that is not clear, let me just write it at the side. F of 1 is 0. F of 2 is 1. And f of 3 is equals to 2. Huh? And let's look at our green machine, our function g. Right? What would g of 1, 2, and 3 would be? Right? Let's look at that. Okay. So I'm not going to write it here. I'm going to write it at the side. G of 1, when we put 1 in, and then we minus 2, what do we get? We get a negative 1. Right? And let's say we put in g of 2, 2, x equals to 2. 2 minus 2 will give us 0. And g of 3 will give us 1. Okay? So what happens when we take f and g and we multiply them by each other? F times g. What happens? Yeah. So, okay, again, I'm not gonna write it here. I'm gonna write it at the side here. What is f of 1 times g of 1? Well, f of 1 is 0. G of 1 is negative 1. 0 times negative 1 just gives me 0. Now let's look at f of 2 times g of 2. Yeah, f of 2 is 1. G of 2 is 0. Multiply together, I get 0. Okay, and let's look at f of 3 times g of 3. F of 3 is 2. G of 3 is 1. So we multiply that here, we get 2. So you can see that, hey, the roots, or where it cuts, the x-axis is exactly where, where it cuts the x-axis for, f of x and g of x, precisely because of that reason, because we are multiplying the two values together. So whenever one of them is 0, it really doesn't matter what the other one is, right? It could have been 10,000 or 5 million, right? When you multiply by 0, you still get 0. And that is why the roots of a quadratic is really the same as its linear components. Yeah, same as linear components. Okay, so I hope that is something very interesting, right? Although I cannot tell you the proof that Gauss has done to prove that, quadratic has two roots, but this is something similar, right? We kind of understand why now we have two roots. Okay, and yeah, we're almost wrapping up roots. So this is the reason why whenever we're given an equation, right, like this, x squared plus 5x plus 6 equals to 0, we are very interested to first factorize this, right? We want to factorize this into, okay, before I write the answer, right, I'm going to give you 3 seconds, or you can pause the video, think about how to factorize this yourself. So the answer is coming out in 3, 2, 1. So this is actually x plus 3 into x plus 2, right? So once I factorize this quadratic into, right, I've broken it down into its linear components, I can tell you that it has roots at x equals to -2 and -3. Yeah, so that is very, very useful. Factorization is really useful because it tells us where the roots are. Okay, so that is going to wrap up roots. I'm going to move on to factorization. Now, moving on to factorization. Now we know why we want to factorize, because we want to find roots. Yeah, so let's look at factorization. Factorization is not new, right? If we talk about factorization, we can recall in secondary 1, we learned about prime factorization. Yes, so let's prime factorize the number 135. Yeah, and you want to prime factorize using this method. I think it's called continuous division. I'm not too sure about the name, right? So here's a cool trick. We want to look at what prime numbers, right, can divide this number. It's an odd number, so we know it can't divide by 2. The next number we probably want to try is 3. And to tell whether it can be divided by 3, we can add all 3 digits together. 1 plus 3 plus 5. That gives us 9. 9 is a multiple of 3, so I know this is divisible by 3. Yeah, so I'm going to put a 3 here. Divided by 3, I'm going to get 45. Okay, I'm going to divide by 3 again. That gives me 15. Divide by 3 again. That gives me 5. And finally, I'm going to divide it by 5 to give me 1. Yeah, something like this. So I can say that 135, this number, can be broken down into its individual ingredients like this. Yes, 3 times 3 times 3 times 5. So this is like factorization. Factorization really is about breaking things down into its simpler parts, which is why sometimes you might hear this term, right? Decomposition, right? We learn it in science, right? Where, for example, when dead matter decomposes, it's broken down into simpler substances. So it's the same thing here. We're taking one big chunk, we're breaking it down into its individual ingredients, right? We can say that 135 is made out of 3 times 3 times 3 times 5. Okay, and the same thing can be applied to quadratic or cubic expressions, right? The same can be applied there. We just seen how to do that, right? With our previous example, where we have x squared plus 5x plus 6. This can be broken down into x plus 2, x plus 3. And that's why this is called factorization. Yes, breaking down one big chunk into its individual components, its ingredients. Yeah, so let's look at factorization. Again, factorization is not something new. We've already done it in secondary 2. In fact, we learned 3 methods to break down a quadratic expression. Okay, if you recall the first one that I just did with you, right? Putting into x plus 2, x plus 3, that is cross factorization, right? Cross factorization. Okay, number 2, right? Number 2, you might be familiar as the one that I shown on the first page of the notes, the meme about Bill Gates playing ping pong with an oversized bat. Yeah, that is using the quadratic formula. Quadratic formula. And the last one, number 3, right? This one is the one that's the least popular, right? It's completing the square. Completing the square. Okay, and here's a spoiler. Here's something that you might not know or may know, right? The 2 of them are actually the same thing, right? They're actually the same thing. Huh? Think of it as Superman in disguise. If some of you know Superman, right? His alter ego is Clark Kent, right? So you have Superman, and then when he's not Superman, when he's just an ordinary person, right, he goes by Clark Kent. So, but they are the same person, right? Just that they appear in different forms. That is our quadratic formula and completing the square. They are actually the same thing, just appearing in different forms. Okay, so yeah, good to review over here. But my question is, why do we need 3 methods, or rather 2? There's actually 2 methods here, but why do we need 3? Right? Why do we need 3 methods when we can just use cross factorization? Yeah. Okay. Right. That's going to be on the next page. Okay. We know that cross factorization is really good, right? From it breaks down, it decomposes your quadratic expression into the linear components, and then we can see the roots straight away. Cross factorization gives us the roots, right? We like that. Huh? But how about completing the square? Why do we need completing the square? So silly, right? Okay, let's look at an example. Like, say if I give you a quadratic expression like this, how would you complete the square? Yeah, we probably want to think of something over here. I need to add something so that I can write this as x plus something square, correct? Yeah? And going by this, say if I have an x plus a square, I should get a x squared plus 2ax plus a squared, meaning that this 12x over here is our 2ax. So if I divide by 2 and I divide by x, I'll get a. Again, if I divide by 2 and I divide by x, I'll get a. Meaning that our a in this case is 6. Yeah, right. I'll probably want to have this. Okay, and in order to make this happen, I need to borrow 36 to make this happen. Yes, if I borrow 36, I need to remove the 36. Yeah, so we'll have this and like that. Okay, so if you're not familiar with these steps, if I'm going too fast, you might want to revise your completing the square. It is a hint, it's rather important in this topic. We're going to use it a lot. Yeah, so please go and revise. So over here, I've completed the square, right? X squared plus 12. Okay, let me just write the original question. X squared plus 12, x is equals to this, equals to this. Complete the square. Doesn't tell us about the roots, right? So if I want to find the roots, how do I go about that? Then I can say that let this whole thing equals to 0. Oh, sorry, let me just say let y equals to this first. And then I can let the whole thing equals to 0, right? When y equals to 0, right? Roots, we can solve for the roots, okay? So then I can say that x plus 6 square will be equals to 36. And then if I square root both sides, remember square root is an operator. There are two possible answers. So you get plus minus 6. And then I'm going to continue over here. That means that x is equals to negative 6 plus minus 6. And this should give you a hint because the way that we have two solutions over here, minus something plus minus square root of something, is very, very, very similar to the quadratic formula. Yes, they are really the same thing, right? So if we go ahead and work this out, you get negative 12 or 0. Those are our roots, yes? Then you ask yourself a question, wait. If I started from here and I use simple factorization, right, I can see straight away the roots are negative 12 and 0. Why go through all that trouble completing the square just to get the same thing, right? So let me answer your question, okay? And why completing a square is very, very important in this topic, right? Is this. Completing a square is not meant to give you the fastest way to get the roots, but it's meant to give you the fastest way to get the maximum or minimum point of this graph. Yes? So one more time. Completing the square doesn't give you the roots very fast, but it gives you the maximum or minimum point of the graph very, very quickly, right? Okay, so here you go, right? How do we tell the maximum or minimum point from here? Okay, so I want you to look at the equation, right, in purple that I boxed it up in purple. Now I'm going to use a highlighter to look at individual components of this equation. Let's first look at this guy here, x plus 6 whole thing squared. What is the smallest value this thing in light blue that I've highlighted can go to? Can it be negative? Is it possible to have a negative value? And the answer is no, because if you take, say, any number, even if a negative number like negative 5, and you square it, you get a positive number. So there's no way this light blue thing can be negative, okay? If it cannot be negative, what is the lowest number that it can go to? It would be 0, isn't it? It would be 0. Yeah, this thing over here, right? The lowest possible value is 0. Lowest. Right? And that happens when the whole thing, whatever's inside the bracket, goes to 0. When this goes to 0, I have 0 times 0, and then it gets 0. Okay? So if this is the lowest value, what is the lowest value of this guy? Negative 36. It is just negative 36, right? So I can tell you that the lowest value of the entire equation is going to be negative 36. Okay? So that is a minimum point, right? Minimum point is going to be some x value, and then it's going to be 36. Okay? Because I know the part in square, the part that's highlighted in light blue, can only go to 0. That's the lowest it can go, right? And when does it go to 0? That's when x plus 6, the thing inside there, is equal to 0. And that happens when x is equal to negative 6. So here, I've worked out the minimum point, -6, -36, straight away from completing the square, right? So yeah, completing the square is very misunderstood, right? It's one of the methods that's not popular at all with students, but we're going to use it a lot because, as you can see, when I'm done with factorization, let's go back to our checklist. Huh? If you look at what's after factorization, we're going to maximum and minimum points. That is really the highlight of secondary 3 quadratic equations. We are really interested in finding maximum and minimum points. Yes, roots can also get us to maximum and minimum points, but it's not as good as the completing square method. Okay, so yeah, I'm going to wrap up factorization. Yes, I'm going to wrap up factorization, and I'm going to explain to you why we are so interested in maximum and minimum points. Okay, and we have an empty page here just to show you why. Okay, now the purpose of learning mathematics is so that we can solve questions in real life, right? And when we do that, we call it modeling, right? Modeling, right? Using mathematics to model real life situations, right? So we are going to use quadratic equations to model real life situations. Yeah, real life situations. So let me give you a very simple situation. Say if I have a garden, right? And I want to use part of the garden to store certain things, right? And say I'm thinking of using forming a rectangular area with some fence, right? I bought fences to fence up an area to store my things inside here. And what I did was I bought 10 meters of fencing, right? So here's a constraint, right? Because the fence costs money, I can't buy an infinite length of fence. I only bought 10 meters, right? 10 meters of fence. But yet I want to have the maximum, right? I want to enclose as large an area as possible to store my things. So then I ask myself the question, how do I get a maximum area using only 10 meters of fence? Okay, so here's how you can do it using mathematics and quadratic equations. First of all, let the breadth of the fence be x. So I have x here and x here. Then what would the length be? What would this side, the length be? The length would be, right, since I bought 10 meters and I'm going to use x on the breadth, I need to minus away 2x. Yeah. And then I have two lengths, so I'm going to take that and divide it by 2. Yes. So that is the length. Now, if I simplify this is very simply just 5 minus x, isn't it? Yeah. The length simplifies to 5 minus x. There you go. So now I have the length and the breadth, right, written in terms of x. Now, the area of this rectangle is going to be x into 5 minus x. Yes? And you can see straight away over here that my roots are going to be this. These are my roots, right? From here, I can tell that the roots are going to be 0 and 5, right? So 0 and 5. Okay, so you can see that it's going to be a brownie curve like that, because if I expand this out, this will be 5x minus x squared. And we know that when the coefficient of x squared is negative, we get a frowning curve, right? And yeah, here's a shortcut on finding the maximum point. Since the quadratic graph is symmetrical, right? Quadratic graphs are always symmetrical, right? Then the maximum point here will be the midpoint between 0 and 5, and that is 2.5. Yeah. So in order for me to build a fence of maximum area, where the area is maxed out, the breadth has to be 2.5 meters, and this has to be 2.5 meters. So if the breadth is 2.5, this will be 5 minus 2.5, which is also 2.5. So you realize that, hey, to get the maximum area out of the fence, I need to build a square fence, a square. That will give me the maximum area. Okay, so without having to build the fence and tear it down, build the fence, measure the area, tear it down and build another one using trial and error, you can use quadratic equations. Saves you a lot of time, right? Just do one calculation and then you can go off on your way to build your fence. Yeah, and you know you're going to get the maximum area. Okay, so this is why we are interested to find the maximum or minimum points, right, of a quadratic expression. Right. So once again, let me just do a very quick summary of what we learned so far. We learned about quadratic expressions. Yes. And then we are interested to find its roots. Why? Why are we interested in the roots? Because the roots can give us the max or the minimum point. Yeah. And yeah, that's why we factorize, right? We factorize to find the roots and it will give us maximum minimum point. Or if you just want the maximum minimum point, you can factorize it straight away using completing the square. Right? Completing the square. Yeah. So depending on what you want. If you want the roots, I will say go ahead with cross factorization. If you want the maximum minimum point straight away, go for completing the square. Yes. And that's why we need two separate methods. Okay. In the next video, I'll talk about, of course, you know, right? There's the third method, quadratic formula. What is it good for? Right? Yeah, basically it's good for finding roots, right? When your roots are not so easily cross-factorizable. Yeah, so that is why we have three different methods to factorize. Okay, so I'm going to wrap up maximum and minimum points, right? We are really interested in maximum and minimum points because we want to use quadratic equations to solve real-life problems. Maximum and minimum points is helpful in that way. Okay, and that makes roots and factorization, yeah, that makes sense. Like why we want to find roots, why we want to do factorize, because those things get us to the maximum and minimum points. Okay, so finally, let's talk about the last part, shifting the graph up and down, shifting the graph up and down. Yeah, so let's look at two different functions, x squared and x squared plus 1. So I'm going to go ahead and go to decimals. I'm going to look at this one. Yeah, x squared and x squared plus 1. So you can see on the left here, the red graph is f of x, where f of x is equals to x squared. Before I click on the second graph, g of x, make a guess, right, what it will look like. So I'm going to review in 3, 2, 1. Yeah, you can see that the blue graph is just above the red graph, right? And it is exactly a distance of 1 above the red graph, okay? So I'm going to compare, say, this point and this point. You see, this point on the red graph is 0, 0. Yeah, when x equals to 0, y equals to 0. This is when x equals to 0, y equals to 1. So the blue graph is 1, exactly 1 above the red graph. Now let's look at the next point when x equals to 1. Sorry, let me just find 1. This is tricky. Yeah, when x equals to 1, y equals to 1 on the red graph. So if the blue graph has to be 1 above, then it has to be x equals to 1, y equals to 2. And we have that. Yes, and let's say if I look at 2, when x equals to 2, y equals to 4, this is x equals to 2, y equals to 5. Now, why is that so? Why is that so? Some of you might be able to see it immediately. If not, you can't see immediately, no problems. Let's think of this in terms of machines again. Yeah, so say if I have a blue machine and a green machine. Yes, my blue machine is f. Remember the fx is this. This is my blue machine. Oops. Let me try and draw this as straight as possible. Box this up. This is f of x. Yeah. And then let's look at the green machine, another machine over here, which I'm going to call g of x. Okay. This is our green machine over here. So if I put in values, say x equals to 1, x equals to 2, sorry, x equals to 2, not negative 2. You know what? Let me just write this properly. X equals to 1, x equals to 2, x equals to 3, right? The corresponding values of f of 1, right? F of 1, since, you know, if you put 1 inside, 1 will be multiplied by itself. 1 times 1 is 1. F of 2 will be 2 times 2, 4. F of 3 will be 3 times 3, 9. Now let's look at the outputs of the green machine, right? What happens when you put 1 in? We have 1 times 1 plus 1. We get 2, right? F of 2 will be 2 times 2 plus 1. So that's 5. F of 3, 3 times 3 plus 1, that's 10. So you can see that, yeah, the plus 1 over here right? Really, it's just adding 1 to the result. In fact, you can think of the green machine probably as, it's really just a blue machine connected to another +1 machine, isn't it? Yeah. If this is our F, right, where it is x squared, then I can have a +1 machine over here. Our machine g of x is really just this, a combination of 2 machines, right? And that's why we have +1. Okay. In fact, you don't have to limit yourself to just +1. You can look at, say, all sorts of values. Let's change x plus 1 into x plus a. And then you add a slider for a, and you can see that, hey, let me zoom this out. And you can look at how the graph is being shifted up or down. Yeah, the graph is being shifted up or down depending on what a is. Yeah, depending on what a is. If a is a negative value, you get shifted downwards. If a is a positive value, it gets shifted upwards. The more positive, the more you shift up. The more negative, the more you're shifted downwards. Okay, and so that wraps up shifting the graph up and down. And I've covered all 6 points on the introductions of quadratic equations. So I hope you enjoyed this video. I hope you can look forward to the next video where I'll be going through maybe some worked examples of quadratic equations. Yeah, the questions that I'll be using is from the textbook. So most of you should be using this textbook. I think it's this one. Yeah, the Marshall Cavendish Additional A-Maths 360. Yes. So I will not be posting images of the question because of copyright issues, but I will just be discussing the questions. So if you have bought the textbook, you can work out the questions together with me, right? So that's the end of today's video. I hope to catch you in the next one. So yeah, see you on the flip-flop.